Howdy and welcome back. So I'm going to plan to just continue on with binary trees, trees with unbound branching, other tree representations, and I'll push binary search trees off until tomorrow. So let's continue on with this discussion today. And I'm going to try my best to introduce this in hopefully a familiar way to how linked lists were and kind of build it up, give you a general ideas, the overarching structure, and then decompose with, okay, how can we kind of deal with, trees of this nature? And then eventually, how can we actually build a tree up to kind of this extent? But if we remember how we introduced the singly linked list, we said we had this node structure and we could kind of had pointers to other nodes. And there's kind of this idea of this recursive data structure. And we just linked them together in memory. So I want to do the same thing here. I want to give you a node structure. I'm going to call it a binary tree node. And it's going to have a pointer to a parent, a pointer to the node on its left, a pointer to the node on the right, as well as some sort of data of type T. From this point forward, everything's going to be templated. We introduced templates a couple weeks ago. So just, we want to be able to hold kind of data of an arbitrary type within our data structures, our collections of data. So that's what we're doing. Now notice here, and I guess I should communicate the essence of a binary tree. That's going to be a tree whose nodes are going to have at most 2 children. So it might have 2 children precisely, such as this root node does up here. It might have 1 child, as this node over here does, or by definition of what constitutes a leaf, we might have a node who has 0 children. Okay, so that's a binary tree. That's the essence of it, binary 2. Okay, so at most 2 children. Let's look at kind of the representation of this. And I'm going to expand upon what I kind of showed you all earlier in that, okay, we'll have this thing. We have these 2 node pointers to the right, another to the left. We have some sort of data. And here's the fun of the accounting of it all is going to be, we also have a pointer up top to the parent. And to highlight these out in the tree structure here, here's our parent pointer. Here's the parent. Here's the left. Here's going to be our right. And notice the diagram from the CLRS Introduction to Algorithm book neglected the data. But I mean, that's not what we're kind of concerned with at this point. We're concerned with emerging the structure. So if we had a binary tree node, and this is a long name, probably should have called it something shorter so I could write it out, but give me 1 second. And again, I'm trying to build this up before we actually encapsulate all of this, kind of the tree structure along with the tree operations into a class, into a binary tree class here. But let's go ahead and look. So I create a single binary tree node over here. Just to save a little bit of writing space, I'm going to go ahead and let the compiler figure out that the type of root is going to be a pointer to a binary tree node of storing elements of type int. And then I'm going to go ahead and just perform some explicit initialization here. The parent, I'll go ahead and assign the null pointer. And because this will be our root, it's kind of always going to point to null pointer. The parent's not going to have, or sorry, the root's not going to have a parent because it's kind of the parent of everything, parent, grandparent, whatever, of great, great grandparent of everything else that's to come. And it just kind of spawned out there. So it doesn't have a parent. The left and right pointers are going to be essentially pointing to null pointer as well because it has no children at this point. And the data, well, I'll give it the integer value of 11. What if I'd like to create, say, a new child on its left? Let me write this out quick. Okay, I know this is a little tight, but here's what's going on here. So I'm going to focus on roots left. Oh, shoot. Roots left. I didn't mean to erase that. So that is going to be assigned the address of a new binary tree node on the free store, which is going to be this object here. Okay, cool. I'm going to say roots left. So we're going to dereference roots left to get us the node there highlighted in green. And we're going to assign to its left pointer the null pointer. That's not a very distinct color. Let's go ahead and go with some orange. So that's what this line here is doing. Roots left, right. So again, we're going to dereference roots left to get us the object highlighted here in green, and we're going to access its right pointer, and we're going to assign to its right pointer the null pointer. So that's what's happening on this line. We're then going to do the same to access its data, and we'll go ahead and give it the integer value of 7. Oops. The last thing we're going to do is we're going to go ahead and point roots left's parent back up to the root to make that connection, back to the parent node. And that's what's going on here. And if you look at this, you can kind of see that, if we were to do the same to the right, or maybe to the roots left and create a new node there, we can eventually have this tree-like structure, this binary tree-like structure begin to emerge. And obviously, we want to go about this, the construction of this in a more methodical way than, stringing together this kind of long, sequence of dereferences. But instead, we'll go from node to node, from hop to hop within this tree by some sort of traversal to get to kind of the area where we're interested in if we wanted to hook in a new node into our tree, kind of similar to how we hooked in a new node into our linked list. And as such, and again, the kind of idea here is this isn't necessarily any more complicated than a linked list at this point, because if you think about it, I mean, we've had kind of two different directions, which is similar to maybe the going left and back to the parent, through the doubly linked list next and previous pointer. The parent pointer is kind of the previous node. So you have some experience kind of with that accounting. The only difference here is that instead of just always going next in this linear fashion, there's a branch and you can go left or right. So you need to make a decision that if you move, from the root node, let me find a color here, from this node to maybe this node, notice that to get there, you had to decide to move right and not left. However, if we want to go back, it's just as easy as following the parent pointer. But this is some additional counting. You've worked with a singly linked list. You saw kind of, okay, if I want to insert something here, I need to be cognizant to ensure, there's no memory links and everything gets absorbed. In the doubly linked list, it was a bit more accounting. I do think having pointers in both directions make the process a little bit easier for some of the operations in a doubly linked list than singly linked list. But irrespective, you had to kind of ensure that the next and previous were hooked up correctly. For the binary tree, we have to ensure that previous, so the parent's hooked up correctly. And then as necessary, we need to ensure that we're accommodating the left and the right pointers as well. The operation almost of, adding into a tree is almost trivial if we're adding just at the leaf. That would be similar to adding at the end of our linked list. We just have to kind of account for who the parent node is. But where the real fun begins, and we'll kind of leave this off until, we won't cover it in 128, you'll cover it in 225, is kind of the ability to get things looking like a tree and not having kind of our tree structure look like a list. So what we'll get into, and you'll see this when I introduce binary search trees tomorrow, is that this tree structure is very desirable but it can diverge to look kind of similar to a linked list. And in that case, you'll have, say, different, more elaborate tree structures than just this binary tree, such as your AVL trees, red-black trees. that will actually rebalance stuff so that essentially all the leaves are almost at the same level. And there's some pretty cool implications of this, which I'll briefly comment on tomorrow, but I'll, defer most of that to 225. And that's where the shuffling really gets interesting. But this is a binary tree. I hope, this isn't too much of a stretch from what you already know. Do fall back on your understanding of the doubly linked list and understand that this is a dynamic structure just like it, except now we're into the kind of nonlinear structure, and that we're creating a hierarchy of sorts, and there is a bit of a direction that we can take from each node. We're not just moving from one to the next. We're actually, branching off, and that branch can have profound implications in terms of which direction you decide to go. So hopefully that was informative. We're going to move into trees with unbounded branching here next. And this and the next will be a bit shorter. Binary trees I wanted to motivate because that will be the topic of the remainder of the week, with a kind of special spin on it in that we're going to enforce some criteria upon this binary tree.